Today I want to make a quick note about quiz 9. The quick note is it's not about finding the area, it's about setting up a definite integral. Or more specifically, describing a region with a definite integral. That would be a better way of saying it. Describing a region with a definite integral. It's about describing a region with a definite integral. So the region that I wanted was this region below this line and above the x-axis. All right. I wanted to describe this a dx and a dy. Specifically, it's the dy that I care about because this is the one. Actually, I need to do both. I need to do both. So this is the equation of this line. It's a proportion and it has a rise of 6 and a run of 10, so y is equal to 3/5 x. What that means is that this line is also x equals 5/3 y. Now, if I draw a dx region, if I draw the dx region, so if I draw a delta x region, I still want to label the x and the y on the graph. So here's x, and here's y. I still want to set up an area of the slice. And since we're doing area in its calculus class, the only area formula we need is length times width. When we're finding area, area is always length times width. Scroll up a little bit. So I can take the width to be the delta x, and then the length is going to be y. So the length is y, and the width is delta x. But I can't integrate y delta x. I need to have a function of x. So I replace the y with 3/5 x times delta x. So here's an expression for the area of that rectangle. Now I just have to integrate all of those rectangles. And the rectangles happen from x equals 0 to x equals 10. So my total area is going to be the integral of 3/5 x. Delta x becomes dx, and we integrate from 0 to 10. Half the area of, so it's going to be 30. I don't actually care about that, but it'd be a good idea for you as the student to check that this comes out to a 30, because that's the area of that triangle. Now, we got to be careful about how we set up the area using a delta y. We're still going to set up area is equal to length times width. But now I'm going to slice using delta y. So I'm going to draw my slice going this way. This will aggravate all the Tetris players because I just put the big, tall, the 4 in a line, like horizontally blocking off this whole 3x3 square. So if you play Tetris, this is just stressing you out because how are you got to clear out all this stuff, you know. So, and in this rectangle, I've got a length and I've got the width. Now, if you use 5/3 y, 5/3 y is this distance here. This is 5/3 y from the y axis to the curve. But that's in the top triangle. The length in the top triangle is 5/3 y. We're trying to find the area of the bottom triangle. I know the areas are the same. That's not the point. If we just needed to find the area of the triangle, 1/2 base times height is what we would do, not all this calculus stuff. So x equals 5/3 y is in the top triangle. I need the area, or sorry, the length from the bottom triangle. Once again, it's not about finding the area of the triangle. It's about describing this region with a definite integral. So although this length is x, I don't care about this length. I care about this length from this x up to 10. So this length, that length is going to be 10 minus x, which using x equals 5/3 y, it's going to be 10 minus 5/3 y. So this is why even though the integral you put with 5/3 y from 0 to 6 gives you the correct area, it's the area of the top triangle, and I wanted a definite integral for the area of the bottom triangle. Once again, because I wanted the definite integral, not the area of the triangle. As a student, this is annoying because you found the problem says find the area of a triangle. You read the problem as find the area of the triangle. That is not what the problem is. The problem is write a definite integral that will give you the area of the triangle. The triangle, not a triangle. You wrote a definite integral that gave you the area of the top triangle. I want a definite integral that gives us the area of the bottom triangle. I don't care that they're the same. I want this one. So the length that we want to use here is 10 minus 5/3 y, and then we'll multiply that by the delta y. And so our area total will be the integral of 10 minus 5/3 y. Delta y becomes dy, and we go from 0 to 6. Now, to make sure that everything is worked out, you should integrate this and find out that this will give you an area of 30. One way to emphasize this, and I guess the problem that I needed to include, here I am learning from mistakes that I've made this semester moving forward, is that I split this evenly. And so we got this triangle. So let's talk about a variation on this problem where it does matter where we put things. And let's take that same rectangle and not split it with a line to make the problem easy, but bend the hypotenuse into a parabola. So let's suppose I'm still going to cut things out of a rectangle, and I can still put this at 10, and I can still put this at 6. But now instead of just connecting the origin and 10, 6 with a line, what if I connect this with a parabola? I'm going to put the vertex at the origin. And let's suppose I still want this region below. Now the bottom half is different than the top half. So now I'd have to come up with an equation for this parabola. It's going to be, it has a vertex at the origin, so it's going to be y is equal to some constant times x squared to make a parabola. We'll be able to turn this around into an x equals. So this would mean x is equal to, we're in the first quadrant here, so I'm going to use the positive square root. The positive square root of y divided by whatever k is. But we still got to be careful about what we want and which half, or whether we want the top or the bottom. If we slice it delta x, then it doesn't really matter because we're just going to be using kx squared. But when we slice delta y, I don't want x. I'm not integrating x. I want this piece here, which is 10 minus x. So in the delta y problem, it matters. Here's another reason that we want to get used to this, setting up this integral where we're making a distinction between the bottom half and the top half of the triangle. Remember, this is not about it's not about finding the area of this triangle. It's about describing this region with a definite integral. We're not trying to learn how to solve this problem. We're trying to understand how we can view this problem through the lens of a definite integral. We're trying to build something, not answer a bunch of questions. We're trying to build a system, not just solve a bunch of problems. Math classes always come out like that we're just sitting here trying to solve a bunch of problems, but we ain't. We're not trying to do it the fastest and most efficient way. We're trying to build a system that we can expand on. We want to build something that we can expand on. This is especially important because some of you are going to be taking Calc 3. Calc 3 is multivariable calculus, which is just Calc 1 and Calc 2 using functions of more than one variable. Mechanically, you have all the skills that you need. We just need to modify them to fit these multivariable functions. So I'm going to draw this triangle again. And I'm going to say some things that will sound familiar. I'm going to draw this rectangle. It's still going to go out to 10 in this direction and go out to 6 in this direction. I'm going to split it down here with the line y is equal to 3/5 x like I did before. And I'm still going to be concerned with this bottom triangle. So let's put some dimensions on this. Let's say this is 10 centimeters and this is 6 centimeters. And let's suppose the density at any point xy, I'm not going to vary the density in the x direction or the y direction. I'm going to vary it everywhere. The density is not just a function of x, nor just a function of y. The density is delta at xy grams per square centimeter. Now we have to make sure that we can describe this region. The bottom triangle, not just any triangle, because the density is different in the top triangle because the density varies with x and y. It doesn't just vary in the x direction, like a single variable calculus problem. It doesn't just vary in the y direction. It varies all over the xy plane. So now I've got to make sure that I'm getting the bottom triangle because the density will be different down here than it is in the top triangle. Now we have to make sure that we're getting the bottom triangle. If we want to find the mass of this triangle, I want to use the fact that mass is equal to density multiplied by area. Mass is density times volume sometimes, but now everything's flat, so mass is density times area. But my density is variable, that's why I don't get to just multiply. If the density was constant, 5 grams per square centimeter, I would just take that 5 grams per square centimeter as the density and multiply by the area, 30 square centimeters, and have 150 grams. But my density is variable. Moreover, the density is a function of not just x, the density is a function of x and y. So now I need to do two integrals. I need to integrate in the x direction. I need to integrate in the y direction. So we're going to integrate the density function. And what we're going to do is instead of a dx or a dy, I know this is from the next class, and you're like, oh, we totally don't care about this. Because some of you are like, well, I don't have to do Calc 3. Haha, suckers. But there's a delta x, and there's also a delta y. So my area is going to be a delta x, delta y. And then I'm just going to calculate the density at that point. And I'm going to assume that the density is constant for this small piece of the area. But now I just have to set up an integral that integrates dx and then dy. So what we're going to do is we're going to set up a double integral. So I'm going to integrate the density. We can do this in a couple of ways. I can do this at delta x, delta y. I can set up an integral that will say dx, dy. Or I can set up an integral that says dy, dx. To do a double integral, you do the inside one first, and then you do the outside one. So we're going to need x's on the inside integral. So this is going to say x goes from left to right. And then on the outside integral, those are the y's. Should use green for that. So if I start from the outside, y goes from 0 to 6. I want my last integral to be constants. Y goes from 0 to 6. If I pick a typical x value, x starts at at one point and ends at 10. So y is 3/5 x. That means x is 5/3 y. So at this point, that's an x. That's the first x we encounter. That happens at 5/3 y. And then we stop at 10. Oh, welcome to your first double integral. This one we set up a dx and a dy. But like I said, we should also be able to do this, set up integrating the density in a dy dx direction. That is, I want the x's to go last. The last one should just be the constants. X goes from 0 to 10. Then the inside one, y starts off at 0. If I pick a typical x, y starts off at 0 and ends at the function. So we'll go from 0 to 3/5 x. Notice that when we take this delta xy and integrate it with respect to y, then we plug in 0 and 3/5 x. So this inside integral is going to give us a function of x that we can then integrate dx. Happens just the other direction in the delta xy. I take delta xy, I integrate it with respect to x, and then I plug in 5/3 y and 10. Now I have a function of y that I can integrate dy with the outer integral. And then we just have to make sure that both of these will give us the same result. If we wanted to find, say, the mass of the triangle. It looks very different what we're doing. But we're just taking stuff that we already know and modifying it to work in this new environment. But to make this skill set work, to build this skill set, we've got to have this one in place. We have to be able to distinguish between the bottom triangle and the top triangle, because it's not about the triangle, it's about the system. And as much as I rail against systems, this is the one that I endorse. And the fact that I rail against other systems and endorse this one, I hope, leads you to believe that I've thought about this system with math stuff. I've thought about this system a lot. So much so that it causes me to reject other systems in favor of one that I know works. I think it's also worth noting at this point, and I've noted this in the past, that mathematics, the idea about how math works, is what the law is trying to be. If we take the idealized form of what the law is trying. If the law could continue on to infinity, if we could apply calculus thinking to the way the law works, math is what we end up with. In math, Euclid's setup is 5 postulates. And even Euclid knew that last one, the parallel postulate, was fishy. It's like, well, this one doesn't have to be, but for my purposes, I'm going to throw in, if you have a line and a point not on that line, there's exactly one line parallel. Even Euclid knew. It's like, we don't have to have this one. We can still have a nice consistent geometry without this, with 0 parallel lines or infinitely many parallel lines. But that's the basis for Euclidean geometry, that parallel postulate. So from those postulates, everything else is derived. He says these have to be true. And moreover, these can't be proven by any system. That thanks to Gödel, we got that. But that wasn't until like the 1930s. But if we start with these 5 ideas, then all these other theorems are derived from those 5 ideas. And this should sound familiar. We hold these truths to be self-evident. That's where it begins. Life, liberty, pursuit of happiness. That's where it begins. That's what the law is trying to be. We're trying to derive all the laws from those postulates. So in a certain point, from a certain point of view, that's why I like math, because math works. But on the other hand, maybe I like math because it's actually simpler, because it works. I don't know. I'm not sure. I'm not sure what the appeal is. It's just that's what the appeal is. It's just appealing. I'm not sure what the appeal is. I just know that it appeals to me. That sense of consistency, the sense of internal consistency. Even though we know logically we don't get to have that without assuming certain things. You know what I mean? So those are the things I recommend that you check out if you're interested in math more than just passing math classes. If you actually care about math as a subject, I would start looking at not only Gödel's proof, also look at Euclid's Elements. Get yourself a copy of Euclid's Elements, probably online. It's thousands of years old. So I'm pretty sure it's got to be in the public domain. I mean, it's thousands of years old. It's like calculus. I don't know why we make you buy a calculus book. It seems unreasonable, because it's not like calculus is like copyrighted material or something like that. I probably shouldn't say this on a recording, because someone somewhere is going to say, oh, I'm going to copyright calculus. And then it'll be just like all those record labels. It's like, we own the copyright on the fundamental theorem of calculus, so you don't get to use it in your video. So there you go, record companies. If you really want to prove that you're most evil of all companies, go ahead and try to copyright, math and stuff. All right, what are we talking about? Just trademark the integral symbol. Make all math YouTubers fight copyright strikes. I don't think it would work if you did it, but if you happen to be a huge mega corporation with virtually limitless funds, then you could easily crush all the YouTubers. It's like going into a poker game versus a billionaire. You're just not going to win. You go all in on every hand, and eventually you'll just lose, and then you're out, and the billionaire is just laughing. You know what I mean? All right. So that's what I had to say about quiz 9. You may want to go out and fix it. You can't use 5/3 y. You've got to use whatever this is minus 5/3 y to get make sure that you're getting the bottom triangle, not the top triangle. Not because it has a different area, but because it's the process, not the area that we care about. That's going to do it for today. And I will see you all on tomorrow. Everybody have a good day, and thanks for playing.